Okay, welcome back to the next lecture on thermodynamics, first law. Okay, Mr. Kwang here again. Okay, so we'll move on with lecture 2, but before we do that, we will look at the exit pass questions from lecture 1, alright? Okay, let's look at exit pass 1 now. Okay, first question was 2.5 kilowatt of kettle that takes 200 seconds to raise the temperature of 1 kg of water from 20 to 400 degrees Celsius, assuming that the specific heat capacity of water is 4.0 kilojoules per kg per Kelvin. What's the mean rate of heat transfer from the kettle to the surroundings? Alright, so let's do this. Okay, so first thing first, we will just work out what is the heat, how much energy is absorbed by the water to raise the temperature up from 20 to 100, and we get 1.0 times 1 kg of water times 4,000 joules of specific heat capacity times the change in temperature of 100 minus 20, so we get 320,000 joules. Okay, next we'll look at how much energy was supplied by the kettle actually. So we just take this 2.5 kilowatts multiplied by 200 seconds. Okay, so this 2.5, did I do something wrongly? Oh no, it's correct. Yeah, so what I've done is that I have tried to find the rate of heat loss by subtracting the power input minus the useful power output. So power input is 2500 watts. Okay, then power that was useful is basically the power that was used to raise the temperature of the water. So I just take 320,000 joules divided by the time taken, 200 seconds, and I just do this subtraction, I get 900. So that's 0.90 kilowatts. Okay, so this is relatively straightforward. Okay, not much to worry about. Okay, this is basically asking to find heat loss. Okay, next we have this question that's a bit more challenging. Okay, I have 100 grams of ice, that's component A, and then at 0 degrees Celsius it's mixed with 100 grams of boiling water, component B at 100 degrees Celsius. You're given the specific heat cap of water, specific latent heat of ice, specific latent heat of vaporization of water. Which of the following graphs best represent the variation of temperature with time of the two components of the mixture? So you have water that's 100 degrees Celsius, and then you have ice that is currently at 0 degrees Celsius. Okay, so they will eventually settle at a temperature in the middle, somewhere in the middle. Okay, but before this can happen, right, the ice needs to melt first. So as this 100 grams of ice melts, right, it will stay at a constant temperature at the start before it becomes liquid state, and then it will start to increase temperature. So that rules out option A and B, because for A and B you can see that the temperature of ice will straight away start to increase, which is not the case in this example here. I want the ice to stay at the constant temperature as it melts first. So that rules out option A and B. Alright, so I can cross this off. Now we have C and D. Okay, C and D, right, the main difference here is, does it settle closer to 100 or does it settle closer to 0? Okay, so is it more than 50 or less than 50 degrees Celsius, the final temperature? So let's look at how we do this. Okay, so let the final temperature be T. Okay, and then the heat gained by the ice is equal to the heat lost by the water. So here, gain by ice is basically component A. Gain by water, lost by water here is component B. Okay, because this is the B was hotter at the start, so B will transfer energy over to A. Right? So if we break it down again, right, this for this side here, right, heat to melt the ice, you need to melt the ice to water first, then heat to raise this new temperature raise the temperature of this new water from 0 to the final temperature. And these two things is equal to the heat to lower temperature of component B. Okay, so we have to write it out in just in algebraic sense, right? This is 0.1 kg multiplied by latent heat of fusion of water, and then multiply by 0.1 C times T minus 0. This is the final temperature. And then on this side here is from 100 degrees dropping down to T degrees Celsius. So that's 0.1. Multiply by 0.1 kg as well, and multiply by specific capacity of water. Okay, if you do this arrangement, you rearrange this equation, what I do is that I basically shifted this 0.1 C and T over to the other side. And I get this term here, and I do one more step. I get this LF equals to C times 100 minus 2T. And then LF over C is equals to 100 minus 2T. Okay, I'm going to rearrange this equation to make T the subject. can see that T is equals to 100 minus LF over C divided by 2. And this number is definitely less than 50 because we know that 100 divided by 2 will be less than 50. And this LF over C is a positive number. So the numerator will be less than 100. And if I take a number that's less than 100, I divide by 2, I'll get a number that's less than 50. So the answer here is actually D. Alright. So if let's say both of them are water, let's say this is 100 grams of water at 0 degrees Celsius, 100 grams of boiling water at 100 degrees Celsius, the final temperature will be at 50 here. Okay. Similarly, if you switch the boiling water to vapor, right, at 100 degrees Celsius, then the temperature will be higher up. Right. So this is quite an interesting question. Okay, let's move on. Okay, next we have a solar furnace of area 0.40 square meters, supplies energy at the rate of 1400 watts per square meter. This one, if you remember, you have learned this under waves, okay, intensity. Okay, below are some information on substance X. Melts at -2, boils at 98 degrees Celsius. Specific heat capacity of the liquid state is 3000 joules per kg per Kelvin. You are given fusion and vaporization latent heat as well. Okay, what is the minimum time the solar furnace takes to heat 1 kg of solid substance X at -2 degrees Celsius to 98 degrees Celsius? This one does not include boiling. Alright. Okay, so let's do this. So your heat supply is used to do two things. One is to melt the substance. Two is to have the gain in temperature of the liquid state of the substance. Okay, so 1 kg multiplied by specific latent heat of fusion, 260 kilojoules. Okay, then times 1 times specific capacity times the change in temperature, 98 minus -2. So this is 100 degrees Celsius of change. Can you do the math? You get 560,000 joules. Then you divide by T equals to Q over P to find timing. So this is intensity multiplied by cross-sectional area, surface area. So you get 1000 seconds. Okay, I think that's all for exit pass 1. We move on to the lecture proper. Okay, so we're moving to lecture 2. So this one, yeah, you'll be wondering how come talk about thermodynamics we have a photo of a soldier here. Okay, actually this rifle, right, this is basically, I think this is a version of AR-15, which is similar to the M16 that we used to use in the army, but now it's we have replaced another rifle. So the boys next time you won't understand. Okay, how this rifle works is actually within the rifle itself. There's this. Okay, your bullets are here. Okay, and this is the piston that hits the back of the rifle, back of the bullet. When this happens, right, the bullet is basically the explosion happens. The bullet is pushed outwards. Okay, but of course, what happens is that the gas that's coming out over here from the explosion, right, is collected by this piston, by this channel here. And once you have that, right, the gas here is under high pressure. It pushes this piston back. When it pushes this back, right, this piston here will move back, allowing the next round to come up. Okay, so this process will continue itself. This allows the rifle to be fired in an automatic state. So that means you just need to hold out the trigger and then your bullets will keep on coming up. Okay, so this is what you're going to see today, kind of. Yep. Alright. Okay, so let's talk about internal energy first. Internal energy very quickly. Usually we use the symbol U. Okay, internal energy of a system is the sum of the random distribution of kinetic energy and potential energies that's associated with the molecules of a system, EK and EP. Okay, we need to be very clear that this is not your typical kinetic energy when the whole container moves. Like if I push a container across the screen this way, this is not the half mv squared that I want. Okay, potential energy is not your elastic potential energy or your gravitational potential energy. Okay, basically I'm talking about the molecular kinetic and potential energy. How much Ke does each molecule have? How much potential energy does each molecule have? Okay, so if I want to find total internal energy, I sum up all the EK and EPs of all the molecules, I get them. Okay, but I think under ideal gas you have learned that there's basically the molecules are all so far apart Okay, you don't have molecules because they are all assumed to be monoatomic gases. Okay, if it's a monoatomic gases, there's no potential energy between atoms, and also because they're so far apart, so potential energy is effectively zero. That means in an ideal gas, all the internal energy is actually just kinetic energy of the molecules. All right. Okay, so we have also learned that the microscopic Ke is associated with the absolute temperature in terms of Kelvin, in measured Kelvin of the system. So Ek equals to 3 over 2 kT. So basically, you just need to, if this will help you find the kinetic energy of one molecule, all right, one atom here. Okay, so this microscopic potential energy depends on the separation of molecules. The greater the average separation between molecules, the greater is its potential energy. The further apart they are, the higher the PE, okay, the EP. Remember, this one is like the G field, G potential graph. As you get closer and closer, the energy will get more and more negative, right? Okay, so we're going to move on to first law of thermodynamics. Okay, from primary school until now, right, we have only learned one way of changing the internal energy of a system, okay, by direct heating or cooling. If I want the gas to gain temperature, I supply heat directly to the system. Literally put a flame below it or put it into a heater. Okay, if I want to cool it down, I put it in the ice bath or put it in the fridge or something like that. So that's the only way to change internal energy of a system so far. Okay, and the first lecture we saw that we did various methods of heating. We also did various methods of cooling as well. Okay, but now we can also change internal energy through mechanical work or by letting the system do mechanical work. Okay, so let's move on. Okay, so defining the first law of thermodynamics. Okay, increase in the internal energy of a system is equal to the sum of heat supplied to the system and the work done on the system. Okay, note the underlying words, right? Because they indicate the direction of energy flow. Okay, so we are always talking about energy coming into the system. Okay, sum of heat Q into the system and then work done on the system. Okay, so delta U equals to Q in plus W on. Heat supplied in the system, work done on the system. Okay. And then basically delta U is the increase in internal energy, Q in is the heat supplied to the system, W on is the work done on the system. So all these have the same energy terms. They are all in terms of joules. Alright. Okay, so let's be careful about the terms. If delta U is positive, that means my internal energy has increased. Delta U is negative, that means there's a decrease in internal energy. Q in positive, I supply heat into the system. Q in is negative, that means heat is lost by the system. Okay, that means cooling has happened. Okay, then we have work done on positive, that means work is done on the system, and work done on negative means work done by the system. Alright, so these terms are very, very important. Please bear in mind that you have substituted in the correct direction. Alright, okay, let's look at work done first. Okay, work done on or by gas. Okay, how do we do it on the gas, right? If we want to do positive work on the gas, right, we use an external force to reduce the volume of the gas. So basically we are compressing the gas over here. Okay, if I want the gas to do work, I let the volume increase. Okay, work is done by gas on its surroundings when its volume is increased due to expansion. Alright, so that means if there's no change in volume, no work is done at all. Okay, this is very important. Alright, this is useful for us later when we look at questions involving change in pressure and volume. Okay, if there's no change in volume, there's never any work done. Alright, okay, so let's look at some definitions first. We have this cylinder here, okay, which is measured by this cylinder of gas here, which is A, and then of course the gas at some pressure is causing a change in volume from this blue color volume to a larger blue plus green volume. So there's a change of delta V here. Okay, remember what we've learned about work done by a force? Work done by a force is the product of the displacement delta x in the direction of the force. Okay, so work done equals to F times delta x, provided they are in the same direction. Alright, so since we have hence work done by gas is by exerting a force F against external pressure. I forgot to label this external pressure here, this PEXT, with change in volume. Okay, so assuming the surface area of gas is A, okay, F equals to pressure times cross-sectional area A here. Okay, since the piston moves at constant speed, this gas pressure P is equals to external pressure here. So W equals to PA times delta, that's negative delta X. Okay, and PA delta X. So P times delta V, because A times delta X is basically change in volume. Okay, once you have that, so you can understand that if your final volume is larger than initial volume, work done by the gas is positive value and vice versa. Okay, so this is the basic equation to remember for calculating work done, assuming constant pressure, very important. All right. Okay, but you don't need to. Okay, I would say that yes, you can be very particular about how you substitute in the values, but you will see that it's actually easier to just go from whether or not it's expansion or contraction, and whether you are trying to find work done on or work done by the gas. So for example, if you are expanding and you want to find work done by the gas, it will be a positive number. Okay, but the work done on the gas will be negative number. Okay, work done and work done by are essentially negatives of each other. Okay, so if I say that I have done this amount of x amount of work, I can also say that negative x amount of work has been done on me. Okay, so again, if I'm doing compression, the work done on me is positive because it's an external pressure pushing me inwards, pushing the gas inwards. Okay, so it's a positive work done, but negative work done by the gas. Okay, then constant volume is of course 0 0 lah. Okay, then how's it important? So if you want to add energy into a system, you compress the gas, because if W on is positive, your delta U will be positive. Okay, if your W on is negative, your delta U will be negative as well, assuming no change in assuming Q is 0 lah, no heat loss or supply, no heat loss or supply to the system. Okay, moving on from here. Okay, let's look at example 7 now. Example 7, I have a sample of gas that undergoes contraction at a constant pressure of 500 kilopascal from 500 cm3 to 200 cm3 before expanding to 600 cm3 afterwards. Okay, complete the table by filling the values of work done on and work done by the gas. Also indicate if the gas has gained or lost internal energy due to work being done. Okay, assuming no Q is 0, yeah? Okay, let's look at this table. Okay, first thing first, 500 cm3 to 200 cm3, work done by gas. This is a contraction. Contraction, right? That means the gas has done negative work. Okay, negative work done by gas. Okay, so basically you find the negative area under the PV graph. Okay, later I see the graph, but essentially here you just take P times delta V. So this is the pressure, 500,000. Okay, then find the change in your volume. Okay, remember to divide by 100 cm3, 2 zeros. Have I missed out 0? I think I missed out. Wait, 100 cm3. I think I missed out 0, right? Let me just quick double check. I'll pause the video to check quickly. Okay, and we are back. Yes, I did make a mistake about the zeros, but yep, just restore this already. So work done by gas, negative work done by gas. So find negative area under PV graph. So just P times delta V. So 500,000 pascal divided by 500 minus 200 cm3, but convert to meter cube. Always deal with SI units itself. Okay, so you get negative work done by the gas, 150 joules. Okay, but if I'm trying to find work done on gas, because in this case the gas is being compressed, so basically I just flip the value lah. Okay, contraction is positive work done on the gas. Okay, so work done on is a negative of work done by, so just negative 150. Okay, 150 joules. So change in internal energy. So I will look at the work done on the gas to find change in internal energy. So in this case, because work done on is positive, is a gain in internal energy. Okay, next from 200 to 600 cm3. This is an expansion. Expansion means positive work done by the gas. Okay, so we use a positive area. So again, P times delta V. I think I copy pasted, but yeah, I need to change this again. I should change it now. Pause and come back again. Okay, and we're back. Sorry, I changed the number, so it's 600 minus 200. Okay, you realize that here, right, I don't really care about which is the positive, which is the final minus initial. I just basically find the change, the magnitude of change first. Then once I find the magnitude of change, I see what I have. I need to understand whether it's expansion or contraction first. So with expansion, and in this case, expansion means work done on by the gas is a positive number, so 200 joules. So it means work done on the gas here is a negative of this number, so it's negative 200 joules. Okay, and then change in internal energy, we look at work done on, so this is negative 200. That means there's a loss in internal energy of the system. Okay, so so far this is quite straightforward. We haven't moved on to the graphs yet. I think that's the next slide that's coming up. Okay, PV diagram. Okay, a PV diagram is what we call a pressure volume diagram. It's essentially a graph that plots the changes of a gas sample's volume and pressure. Okay, so how do we draw a PV diagram? We basically, anyway, once you have a PV diagram, right, we can do a few other things. We can make further calculations of the sample's state properties. We can find mass, temperature, internal energy, etc. Depends on what is given to us. Alright, so this is how a PV diagram looks like. Okay, basically I plot pressure on the y-axis and then volume on the x-axis. Okay, the units will be dependent on what you're going for. So in this case, I have in kilopascals and for cm cube. Okay, so let's look at how to draw a PV diagram. Okay, first we have a sample of gas. So we have this gas 500 kilopascal, 800 cm cube. So we plot it according to its position. Okay, this sample is at 500 kilopascal, so it's here. 800 cm cube will be at here. Okay, next we're going to compress the gas. We're going to compress it from 500, compress at a constant volume, 500 kilopascal to 500 cm cube. So 500 kilopascal is still here, 500 cm cube is still here. Okay, next we'll do one more compression. We'll do 200 kilopascal and 300 cm cube. So right now I'm reducing the volume of the gas and also reducing the pressure. Okay, note that this one I haven't taken into account what the Q and W is. So Q and W will change and then you affect its position on this PV graph. Okay, so later you can see how we can use this to calculate, let's say Q or work done, etc. Okay, so this is how you plot. So basically you just translate, you just take each point's PV value and then plot it on the graph. Alright, okay, then since we know from the previous chapter that PV equals nRT, so for ideal gas you have your pressure and volume and then you have the number of moles multiplied by your universal gas constant 8.31 and then multiplied by your temperature in Kelvin. So PV is nRT and N is R for nR is constant for a fixed sample of gas. You don't change the number of moles of gas once you start experiment. So PV is proportional to T. So basically, right, by changing temperature, I will affect either P or V value. So that means I can find different values of PV to satisfy the same temperature. Okay, for example, you look at this 500 times 800, right? So this is 5 times 8, I get 40, right? I can get the same outcome by having like 1000 kilopascal and 400 cm cube. This will give me the same temperature as well because the PV value is the same. Okay, so that's how I can do it. And this 200, 300, I can get the same temperature at 100 and 600. Okay, it will work as well. Right, so this is useful. Later we can see for what we call isothermal changes. Okay, let's move on. Now let's start to look at work done. Just now when I said area on the graph, this is what I was referring to. So since A to B and B to C are contractions, it's positive work being done on the gas. Okay, if I want to find the work done on the gas from A to B, this is basically the area I'm after. Alright, and I can do the calculations. A to B, basically I find area on the graph. So 500 times 10 negative 10 power 3 over 800 minus 500 times 100 divided by 100 power 3. Okay, 150 joules. Okay, so this one, positive work is done on the gas. That means negative work is done by the gas. Okay, next for B to C, we have this shape here. This is essentially a rectangle plus a triangle on top. Essentially, you can treat it as a trapezium. So you can use whichever method you prefer to do. I think I treated this as a normal, just a rectangle plus a triangle on top. Okay, so I got about 70 joules. Alright, so this is also positive work because the positive work is done on the gas, okay, because it's compression. Note that I say positive work is done on the gas. I have to say the same thing because if I just say, oh, it's a compression and it's positive work, and positive work is done, okay, I need to say it's on or by the gas to be very, very clear. Alright, moving on. So calculating work done, essentially, if you look at this movement, if I go from a larger volume to smaller volume, this is compression. That means positive work is done on the gas. If I go from this smaller volume to a larger volume, positive work is done by the gas. Alright? And essentially, your work done is area under the PV diagram. If those of you who are okay with your integration, basically finding area under this graph, okay, you can integrate this. Alright, so let's go on. Okay, so let's look at, we reference to the graph below, determine the work done on the gas when the system undergoes a thermodynamic processes of A to B to C. Okay, we have done it just now. So I just take it from here, 150 and 70 joules, just add them up. Okay, total work done system is 220 joules. W on is 220 joules, alright? Okay, next you are told that there's a total increase of 340 joules in the internal energy of the gas due to the processes A, B, and C. Determine the total amount of heat supplied to the gas during this process. Okay, so we look at this equation again, this first law equation. This tells us that to change internal energy, I can either supply or take away heat, do work on the gas, or let the gas do work. Okay, so I sub in the values. This is decrease in internal energy of 340 joules. So this is negative 340. Q in is what I want to find. W on is 220 joules. Okay, so we just do the calculation. Realize that Q in is a negative value. The system is giving out heat as you do this process. So basically, as you do the compression, what's happening is that you're allowing the system to lose heat as well. Alright. Okay, so negative 560 joules. This is a heat loss. Right? Okay, we have come to the end of this lecture. This is now exit pass 2. You can go ahead to do exit pass 2 now. Remember, like I said, if you have not done well for this year, but somehow you have made it to JC2, it's really, really important for you to keep focus on your lecture series this November and December period of time. Okay, so please try the questions before you watch lecture 3. Alright, that's all we have for today. Thank you.